Hello students, the next type of oscillator is an RC oscillator. Last time we have studied about LC oscillators. So in LC there are two types of oscillators, Hartley oscillator and Colpitt's oscillator. So the next type of oscillator is RC oscillator, and in RC type there are two types of oscillators, RC phase shift oscillator and Wien bridge oscillator. Okay, so first of all we will study about RC phase shift oscillator. Okay, so in RC phase shift oscillator there are three RC networks. There are three RC network, and each RC network produces a 60-degree phase shift, and this can be RC phase shift network produces 60-degree phase shift, and this can be calculated by using this formula phi is equal to tan inverse 1 upon 2 pi FCR. By using this formula, the phase angle is calculated. So each RC network produces a 60-degree phase shift. Therefore, since there are three RC networks, therefore the total phase shift is 180 degree, and this is a common emitter amplifier. So using transistor, therefore this transistor amplifier produces again 180 degree phase shift. Thus the total phase shift becomes 360 degree, and therefore this circuit is capable of producing oscillations. This RC phase shift oscillator produces oscillations, or it acts as an oscillator. This circuit acts as an oscillator because each RC network produces 60-degree phase shift. Okay, this can be calculated by using formula phi is equal to tan inverse 1 upon 2 pi FCR. Phi is equal to tan inverse 1 upon 2 pi FCR. This oscillator consists of three RC networks which are called as ladder networks. There are three RC networks which are also called as a ladder networks, and the transistor works as a common emitter amplifier, and it provides 180 degree phase shift. This transistor amplifier provides 180 degree phase shift, and the phase shift provided by each RC network, it is given by phase shift provided by each RC network, it is given by the equation phi is equal to tan inverse 1 upon 2 pi FCR. Okay, so each RC network provides a phase shift, and it is given by the equation phi is equal to tan inverse 1 upon 2 pi FC into R. Okay, the phase shift provided by each RC network, it is given by the equation phi is equal to tan inverse 1 upon 2 pi FC into R. And if all the capacitors are equal, if all capacitors all capacitors are equal, and if all resistors are equal, that is R, then the total phase shift of the RC network will be 180 degree. The total phase shift of the RC network will be 180 degree, and this is a common emitter amplifier. This common emitter amplifier produces again 180 degree phase shift. Thus the total phase shift becomes 360 degree or 0 degree, and therefore this circuit acts as an oscillator. Okay, but the gain of the amplifier must be sufficient so that A beta should be greater than or equal to 1. A beta should be greater than or equal to 1, and the gain of the amplifier must be sufficient. The gain of this amplifier must be sufficient, and the A beta should be greater than 1. Generally, the gain of this amplifier is greater than or equal to 29. Okay, and the frequency of the oscillations FO, that is output frequency, is equal to 1 upon 2 pi RC root 6. FO is equal to 1 upon 2 pi RC root 6. Okay. The advantage of this oscillator is useful to obtain a wide range of frequencies from few hertz to some kilohertz. Okay. And the drawbacks of this oscillator: the frequency of oscillations cannot be varied easily. The frequency of oscillations cannot be changed or varied easily, since it is difficult to vary three capacitors. It is difficult to vary three capacitors simultaneously. The since the three capacitors cannot be varied simultaneously, since these three capacitors cannot be varied simultaneously, and therefore the frequency of oscillations cannot be varied easily. Then next, gain of the amplifier must be high. The gain of this amplifier must be high to overcome losses in the RC network. To overcome the losses in the RC network, the gain of the amplifier must be very high. The gain of the amplifier must be high. Then third, the frequency stability. The frequency stability of this oscillator is excellent or very good. The frequency stability is very good, and this oscillator is useful for the frequencies below 10 kilohertz. This oscillator is useful for the frequencies below 10 kilohertz. Below 10 kilohertz. Okay. Now the next type is Wien bridge oscillator. Wien bridge oscillator. This is a Wien bridge oscillator circuit. Here the feedback is given to this RC network, and there are two stages of amplifiers. These are two RC coupled amplifiers, and these RC coupled amplifiers are cascaded with each other. The output of first stage, it is given to the input of second stage, and this is RC coupling, so this is called as RC coupled amplifiers. So there are two RC coupled amplifiers in Wien bridge oscillator to obtain sufficient gain. Then the output of second amplifier, it is fed back to the input of first stage. Now see here, this is a RC oscillator. Which is useful for generating low frequencies in the range of 10 Hz to about 1 megahertz. This Wien bridge oscillator produces the frequencies from 10 Hz to 1 megahertz. This oscillator consists of two stages of RC coupled amplifiers and a feedback network. There are two RC coupled amplifiers and there is a feedback network. The output of second stage of amplifier, it is given back to the feedback network. The output of second stage of amplifier, it is given to the feedback network, that is to the RC circuit, and the voltage across the parallel combination of C2 and R2 is given as input to the first stage. The output of the voltage across the parallel combination of C2 and R2, the voltage across the parallel combination of C2 and R2, it is given as the input to the first stage. The voltage across C2 and R2, is given as the input to the first stage. As each amplifier stage provides a phase shift of 180 degree. First amplifier provides a 180 degree phase shift, and again the another amplifier stage provides again 180 degree phase shift. Therefore the total phase shift becomes 360 degree. Or 0 degree. Okay. As each amplifier stage provides phase shift of 180 degree, the total phase shift is 360 degree or 0 degree. phase shift through the coupling network is 0. The frequency of oscillations is given by the equation FO is equal to 1 upon 2 pi RC. The frequency of this oscillator, the frequency of this Venn bridge oscillator, it is given by the equation FO is equal to 1 upon 2 pi RC. Okay. Then a negative feedback is also provided by R3 and R4. Negative feedback is provided by R3 and R4. These R3 and R4 are used to provide a negative feedback, and since a negative feedback is used, this improves the stability and keeps the gain within limits, and so that A beta is equal to 1. This improves the stability. Since negative feedback is used, then this improves the stability of oscillations, stability of frequency, or we get stable frequency with constant amplitude due to the negative feedback. So this R3 and R4 provides negative feedback, and therefore we get stable frequency, or this improves the stability. That means we get stable frequencies, and it keeps the gain within limits. So that A beta is equal to 1. A beta is equal to 1. The frequency can be varied. The frequency of oscillations can be varied by varying the two capacitors simultaneously, by changing the capacitance of C1 and C2 simultaneously, because this is a gang capacitor. So in gang capacitor, the capacitance of C1 and C2 simultaneously varied. It is simultaneously varied because this is a air gang capacitor. Therefore, the capacitance of C1 and C2 can be simultaneously varied. Okay, and therefore the frequency can be varied using these two capacitors C1 and C2. Okay, so we will stop here.